Okay, so thank you very much. Yeah, so let's see. Last time we were talking about the L example. So we were trying to see how to concretely compute. Well, this is not quite a square with the same proportions. Okay. And then we wanted to understand the action of this matrix here on homology. And for that, we selected a few cycles. So one of them was the cycle here. I called it sigma 1. Then another one was this guy here, sigma 2. Then zeta 1 and zeta 2. So the first thing that, so I mentioned yesterday that this set here is a basis of homology. So let me give a name for this origami, L. And I left this as an exercise, and I gave a hint, so it's an exercise. And the hint was to use intersections. We use the intersection form. And by this I mean, so why sigma 2 is not a multiple of sigma 1, so why these two vectors are independent? And the answer was, well, sigma 2 intersects zeta 1 with plus 1. And so by this equation, this should be lambda times sigma 1 zeta 1. But sigma 1 and zeta 1 have no intersection, so this would be 0. And you can keep going like that to check that all these cycles are independent by finding other cycles which intersect some of them, but not intersect a part of the basis, but not the other. So this allows you to check linear independence. Okay, so this is the basis. Actually, just let me make a remark that using my notation from yesterday, I defined a cycle sigma, which corresponded to summing all horizontal sides of all squares. Right? And in this case, sigma is simply sigma 1 plus sigma 2. Right? Because actually, this side here, since these two guys are identified, this cycle is homologous to this one. So this is sigma 1, and this is sigma 2. And I sum it all over bottom sides.
And Carlos, can you just remind us which vertices are identified?
All of them are, I mean, all exterior.
But then sigma 1 and zeta 1 do intersect.
In this picture?
Sigma 1 and zeta 1.
No. No, this guy is coming from this point to this point. And this guy is going to, how they intersect, I don't see.
If all the vertices are identified?
No, they're not passing through the vertex precisely. I'm choosing representatives which are slightly below. And these guys are homologous.
Okay, I didn't.
So the key point is that's a good question actually. When you try to compute intersection forms, you should avoid taking representatives passing through these conical singularities. Because on the conical singularities, so the point is that if you take the representative which is sitting precisely on the conical singularity, then actually for sigma 1 and zeta 1, the local picture is like that. Sigma 1 comes like that, and zeta 1 goes like that, locally. So actually you can detach on the surface. So this is why it's a bad idea to compute intersections with representatives going through the conical singularity. Sometimes they cross, sometimes they don't, and so it's hard to decide because there is too much angle around. So this is why I took this cycle and I did a little movement, which keeps in the same homology class, because these things bound a surface. And yeah, and then by moving a little bit down and a little bit to the left, we see that they don't intersect anymore. Okay.
So what is the sum of sigma 1 and sigma 2?
Sigma 1 and sigma 2 is the cycle that I defined to be the sum of all bottom horizontal sides of all squares. So this was defined last time. So and similarly, zeta is in this case zeta 1 plus zeta 2, and so these two guys span the plane, the tautological plane. I called it H1 ST for standard. Okay. Now I want to continue to tweak a little bit this basis. So I'm taking these two vectors now to be the first two elements of my basis, because I like them better for a reason that I'm going to explain in a moment. Once I get these two vectors, I'm going to produce a basis of this space that I call it H10. And for that, I told you that the idea is that H10 consists of all cycles whose holonomy vanishes. So of dz should vanish over the cycle. So a quick way of doing this kind of things is you can take sigma to be, you go once through sigma 2, and then twice sigma 1 in the opposite direction. Why? Because the holonomy of this vector, so the integral of dz over this guy is 2, 0. And so if you do this twice minus twice 1, 0, you get 0 for the integral. Similarly, you can define a big zeta vector, which is the difference of this guy minus this guy. Zeta. And this is a basis span. So spans the H10 subspace. So the space of vectors with zero holonomy, or if you wish them. Big zeta, so it's a big Z. Zeta 2 minus 2 as zeta 1. Okay, so this is my new basis, and why I'm putting this basis is going to be clear in a moment. So for now, let's just do the exercise of computing t squared acting on these cycles, and then we're going to change basis. Okay, so for now we have two bases. Sigma zeta, big sigma and big zeta is also a basis of H1LR adapted to this decomposition. Okay, the first two are the first part, and the second two. And you're going to see why this is interesting. But let's compute t. So t, the idea to compute t is that you should not be greedy. So you don't need to look at the action of t on the whole surface all at once. What we're going to do is something called cylinder decomposition. So cylinder decomposition, which is simply the following. In this case, we are going to look at the horizontal direction, and we are going to collect all horizontal geodesics which are parallel until they hit a conical singularity. So one cylinder, we can see it's here. If you take this collection of parallel geodesics, horizontal geodesics, they fill a little cylinder precisely because these sides are identified. And the maximal collection is just this square, because when I start taking all parallel guys together, they hit the singularity precisely here. So there is one cylinder, which is the red cylinder, which is this one, which is just a square. And there is another cylinder, which is the white one, which is actually this thing here. Okay, so there are two cylinders. So I'm just decomposing my surface into two pieces to analyze it better. Okay? And actually, this side is identified to this side. So now that I want to understand what t square is doing to each cylinder. And actually, this is the action of t square, and actually any matrix of this kind, of parabolic matrix of this kind, act on cylinders by then twists. So this is a word that you heard from Javier's talk. So thank you, Javier, for saving me some time. So these are then twists. So what is the point? The point that if you look at this curve in the middle, let me put a red color. So I'm doing a really complicated. So take this curve in the middle, which is actually in the homology class of sigma 2. So if you apply T2, you are going to slant this cylinder all over the way like that, right? And this side, this middle square is going like that, and I didn't feel something like that, and right? And this curve is there. Now, remember that we are talking about translation surface, so you can cut and paste. So if you cut and paste back this piece here, we find the same cylinder back. So the names are that and that. And the same curve in the middle. Right? So if you cut and paste the cylinder, you get the same cylinder back. Actually, the magic formula is that if you have a cylinder of height h and length l, and you apply the matrix 1, k, actually any multiple of l over h, 0, 1, then you are going to slant this according to multiples, and you can cut and paste to get the same cylinder, actually. Yes?
Where does the matrix come from?
It's just an example. It's just an example. I'm computing the action of T2. I chose this matrix because it belongs to the Veech group. So I know that.
Arbitrary. It didn't appear before. Oh, okay.
Huh?
It didn't.
No, it's just an example. I'm doing an example. I'm doing an example. It's just an example. I mean, you can choose your preferred matrix and do the same calculations. Yes. I prefer this one because it belongs to the Veech group. So, in other words, this cut and pasting is perfect. It's going to work. I'm going to get the same surface back. If I did just t once, it does not work.
It's a part of that SL of O.
Exactly. This matrix belongs to SLL, the Veech group of L. Okay, so now this was defined last time, so I'm not going to define again. I'm sorry, but I need to advance. Okay, so let's see. Now, so this is, so sigma 2 does not move. That's very nice. So we understand how T2 acts on horizontal cycles. So T2 of sigma 2 is sigma 2. Very nice. And what happens to a little curve that goes around, say, from top to bottom, like that? So this curve, you see that when you slant this thing, it goes like that, right? Yeah, so like that, say. And then you cut and paste. And so this means that this curve is doing something like that. Yeah, it should cross at some point. It's kind of here and yeah. Right? And so this means that any curve trying to cross the cylinder from bottom to top, say. So let me call this cycle gamma. So T2 of gamma is actually gamma plus sigma 2. So it goes up, except that it gets a little hit by this curve and then goes up again. So it's basically trying to go up, except that you should add one turn. If you had more powers of this guy, like here, you add k times this curve. Because you are slanting this more and more, and so when you cut and paste, cut and paste, cut and paste, you are doing more and more times. So in Javier's notation, here is sigma 2 was called alpha when he was explaining. And this cylinder is what he was calling the safety neighborhood. So this is his n alpha in his notation. And so we are doing the twist here. Of course, you can do the same process here. And actually, the formula, so I'll let you imagine what are the formulas, but it's not very hard. So what happens is, T2 of sigma 1 is sigma 1. I mean, sigma 1 is horizontal, so it does not move. But a curve, well, I don't have, not high enough to draw a little curve. But imagine that there is a little curve crossing that cylinder, call it delta. T2 of delta would be delta plus, well, twice sigma 1, because sigma 1 is a cylinder of size 1 by 1. So when you apply T2, actually you should cut and paste twice to get the same cylinder, the same square. So this means that you are turning twice. And so these are the formulas. So from this we can compute the formulas for T2. So this implies that T2 acts on sigma 1 by sigma 1, on sigma 2 by sigma 2. So this is normal because it's a parabolic matrix fixed in the horizontal direction. And on the vertical, what you do is sigma 1. So sigma 1 is this little cycle here, right? So you see that it crosses the cylinder just once. And so it gets to sigma 1 plus zeta 1 plus sigma 2. And T2 sigma 2 is zeta 2 plus 2 sigma 1.
The labeling was different. What is zeta 1?
These are the cycles drawn there.
You said big zeta is zeta 2 minus 2 zeta 1.
Yeah, but these are still the zetas. So I'm just analyzing what happens to the zetas.
Yeah, so. Yeah, but. Okay. Well, I feel like zeta 2 is twice as long as zeta 1. Yeah.
No, but I'm thinking of zeta 2 as a little path which is crossing each cylinder. So zeta 2 is a path which crosses the first cylinder, which is 2 by 2. So actually, gamma is a little piece of zeta 2. So when this piece crosses, it gets hit by sigma 2. And when it goes further up, it gets twice sigma 1. So this is what I wrote here.
Look at that to be added.
Here in homology.
Oh, it's. Oh.
This is a calculation homology. We are computing action on homology. And so you see that in the other basis, sigma goes to sigma. T2 of zeta is C zeta plus 2 sigma. T2 of sigma is sigma. And T2 of z is what happens to zeta 2 minus twice what happens here. So it's this minus twice that. So it's z. This minus twice that. So minus sigma. Right? So in this basis, the matrix of T2 acting on homology is simply 2 blocks. So I'm ordering my basis to be sigma, zeta, sigma, z. So I'm putting the images of column vectors like that. So this is 1, 2, 0, 1. And here is 1 minus 1, 1, 0, right? So in this basis, you see that actually this matrix respects this decomposition into standard, and so these blocks don't talk to each other, which was announced by me. I was telling that the action on homology preserves. So this is a general fact. So actually, I'm going to come to this point later. And also, there is an important point for those who know that minus 1 in modulus is less than 2. So actually, this part is lower than that part, and this is normal. This is the case always. I mean, there is a sense in which you can formalize this thing, that the action on H10 is always lower than the action on SU1 standard. And actually, of course, we did that for the L, but there is a generalization of this construction called the Kontsevich construction. So actually, what I did here is just an example of the keyword is Kontsevich construction, which is just you build surfaces by piling up cylinders, and then you understand first the action of these parabolic elements, and then you get usually a big subgroup of SL2Z, thanks to the action of these two parabolics. I mean, usually little parabolics generate subgroups of SL2Z. So this allows you to put your hands on many actions of affine guys. So this is the example. So this example generalizes to in the theory by, so the point is that in general, we have a representation rho from the affine group of homeomorphisms of an origami into the symplectic group of symplectic automorphisms of the homology. Symplectic with respect to the intersection form. So this is the point. So this is action on homology. Actually, last time I gave you formulas for how T and S, the usual parabolics, act on relative homology. From those formulas, you can check that rho respects the composition H1 standard plus H10. So so in particular, this representation is reducible, not irreducible, if you wish. So this block decomposition is always there for abstract reasons. Also, it's kind of funny that actually, so this is one remark. Another remark is that rho restricted to H1 standard actually is the action of the Veech group in the basis sigma zeta. And we saw that here. I mean, what I mean by this statement is that if I take T2 and I restrict to this plane, the matrix that I see is the same matrix. It's itself. So it acts by itself on H1 standard. So this is why we call it tautological action, because it's the action that we already see from the linear part.
So automorphisms don't act.
Automorphisms act.
But not on H1 standard.
Yes, on H1 standard. Yeah. Trivially. Yeah. In H1 standard, the action is trivial because automorphisms are translations, so they are just changing names of squares. But since sigma is a sum of all squares, permutation doesn't matter. Yeah, so it's identity on yeah. I mean, if
the genus is larger than 2, H1 standard is always dimensional 2.
Yeah, so what happens here is that the example I chose is genus 2. So the homology has dimension 4, which is not, so it's normal that my action is 4 by 4 matrix. In general, this thing here has dimension 2. So this is 2-dimensional. And this is what you need to complete. So 2G minus 2 to get the full 2G. So this representation is tautological at the level of H1 standard. And usually the interesting part, I mean the new part, comes when the genus increases, because then you get interesting matrices here. And
What's the name of the second one, H10?
it's the space of zero holonomy vectors. So this is one name. Zero holonomy vectors. This is one name, but it goes under several names. So actually, the restriction to the, if you wish, in this context, the restriction to H1 standard, to H10, is what people call the Kontsevich-Zorich cocycle or Kontsevich-Zorich monodromy. Okay, and why I'm calling this monodromy? So maybe I'm going to take this in Blackboard so that you have time to take notes. So where is the eraser? Ah, it's here. Okay. Okay. Ah, yes. So this is not very smart because it's going to. Okay. So why I'm calling this monodromy? The key point is that I'll try to avoid this. Maybe I should keep going so that the other part will get. I can use it later. So the name monodromy comes from the fact that there is a nice construction. So every time you have a representation like that, you can build. So the big names, if you wish, are local systems. If you come from algebraic geometry, so local systems. And then you might want to use Gauss-Monning connection. So I'm just giving keywords. I'm not going to define them. So don't ask me what this means. I'm not going to answer. I'm just giving you words so that you can go to Google. And then if you are interested in this, you can read more. So Gauss-Monning connection. What more? Hodge bundle. So these are some keywords which are behind this construction that I'm going to show. Gauss-Monning connections, yeah, and variations of Hodge structures of weight 1. And etc. I mean, there are many key big words here. Of course, Kontsevich-Zorich, cocycle, I already mentioned, but yeah. So these are some big names. So, but these are big names for the following construction. So the idea is that first you can start with the so SL2R will be our phase space. So SL2R is going to play the role of the Tashimoto space for us. For origamis, you don't have to look at complicated Tashimoto space. It's just SL2R, and you can build the trivial bundle by taking the product with the homology. Okay. And on this trivial bundle, you have an action of SL2R precisely, which is the action that for each couple G homology class, you take an element H of SL2R, and then you multiply the matrices, and you keep the same homology class. So it's multiplication on the first coordinate and totally trivial on the second. So nothing happens, it's not very interesting. And now what you do is you go to moduli space. So in other words, you take the action of the affine group of the origami on both sides. So this is the diagonal action. So what is the diagonal action? Well, the linear part acts by multiplication here, and the affine homeomorphism acts on homology. So this is the diagonal action with those two guys at the same time, both on G and C. So at the same time that you change G, you also change C. So actually, the non-triviality comes from this part of the quotient, and this is what. So the picture is the following: the quotient of the first piece by that is just the quotient of SL2R by the Veech group, and this is a Riemann surface, so it's something like that. It's a hyperbolic Riemann surface with some cusp, some genus. I don't know precisely, but it's something like that. Certain number of cusps, and so this is SL2R mod this guy. At each point, you are putting a fiber which is a copy of the homology. And then what you say is that you can run SL2R. So for instance, you can run GT, so this famous matrix which is exponential t, exponential minus t, to go around this hyperbolic surface. I don't know. You go around and you have fun. Then at some point you get back close to where you were. And when you get back, the point is that you can, getting back, I mean, if you get exactly to the same surface, this means that there is an affine homeomorphism allowing you to cut and paste. I mean, this matrix is just deforming the polygon, like we did with T2, etc. And the fact that we say that we get back to the same means that we can cut and paste to get the same surface. But cutting and pasting is just an action on homology. So actually what happens is that when we get back to this, at the level of the fiber, we get back by some matrix, which is precisely the matrix row of the element that we are going to use to identify. Sure? Yeah, it's always, in cases, yes, it's always non-compact, but it's finite volume because for origamis, for instance, this is a finite index subgroup of a set to Z.
But it's not necessary.
Huh?
Finite volume for the general Veech group?
No. In general, yes. I mean, the Veech group of a general translation surface, yeah. Here, I'm talking about origamis. So I know that the surface is like that because this is finite index in a set to Z. Yeah, you're absolutely right. Yeah. Yeah, there are many. Yeah, typically the Veech group is trivial, so you don't close. I mean, the orbit gets dense, and yeah. But I'm talking about a very gentle guy, which is it happens that its orbit is closed, so everything is very nice. I don't have to look at all Tashimoto spaces, just this little piece. And so this is why the theory is simple. In general, I have to replace this by moduli spaces and the Hodge bundle. So this is I'm telling these big names. And then what I'm doing here is a parallel transport with respect to a certain connection, which is the Gauss-Manning connection. And this is a very interesting parallel transport because homology decomposes into H10 and 01. So it's Hodge decomposition, and which is useful to keep in mind when you are doing arguments with this object.
Can you repeat again, please, what is the fiber?
So the fiber is just copies of the homology. For each surface, you put the homology. And then, yeah, so this is a way of keeping track of cutting and pasting when you move. You don't forget. I mean, in moduli space, you say that two surfaces are the same if you can cut and paste, but you don't care how you cut and paste, I mean, to be the same. But here, you are more or less caring on how you cut. You don't keep the full information on how you cut and paste, because the full information is the element of the affine guy. It's the mapping class. But you keep just the information at the level of linear algebra, so which is the action on homology. So it's like in topology that you have complicated varieties, and you attach homology precisely to be able to study the topology of the object, because linear algebra is easier than nonlinear objects.
So, can you
Yes?
say again how what GT has to do with this?
GT is just an example on how we can use SL2R to move in the surface. It's just one example. You can.
By construction, the element of the quotient of the affine group will correspond to loop. But, I mean, why is this loop realized by GT?
No, GT gives you a deformation, and of course, I mean, it's hard to figure out which element. So this is a point. It's not obvious at all which element of the affine group you are picking when you are closing. I mean, the fact that I'm saying that it's closed, I'm telling you for miracle there is an oracle which tells me that this orbit is closed. So being closed by definition means that there is a way of cutting. But the way of cutting, so the way I'm picking an element here is highly non-trivial. And so this is why the theory is difficult, because, yes?
You're describing now the action of the genus flow.
Exactly.
You described?
Yeah, exactly. I see.
I just
Yeah.
wanted to say that your previous example, closely related to the famous horizontal flow.
Exactly.
Which is.
Yeah, I'm going to write that. Yeah, exactly. So actually, so this is a very, yeah. Thank you very much. I mean, this is much easier. So what I did last time was with the example was the following. I had my origami L, and then I started applying what is called the Eurocycle flow. Thank you very much. So in this case, I'm taking this matrix, this family here. Okay, this family of parabolics. So if I apply this matrix, then I'm moving on this surface. And actually, I told you that when S equals 2, I close up. I get to the same origami. So this is T2 equals itself. And what I'm saying is that when I came back, I'm cutting and pasting somehow. And the matrix and homology that we get is precisely this matrix here. that I erased it. Yeah, it was here, I guess. Yeah, that's unfortunate, but yeah. But you see, you get it. Yeah. So we do this loop here around this cycle. What you get is precisely that matrix. So this is what we are talking about. So representations actually give this by this construction flat bundles and yeah. And so this is the maybe you can make a break right now of 10 minutes, I guess, and then come back, because then I'm going to shift a little bit the subject to study this Kontsevich-Zorich cocycle, and so things are getting tougher. So I think you need a little bit of fresh air before I I proceed. Sure. Okay, so let's get back to where you were. So I think I defined more or less for you what is this Kontsevich-Zorich cocycle. And now, actually, so this is a very classical construction. I mean, every time you have a representation like that of the pi1 of some object, that actually can build such a locally constant monodromy and a flat bundle and things like that. So this is very classical. So this is just one example. So let's try to analyze this cocycle for a moment. Then I'll tell you one application on why you should care about this cocycle, but not now. So let's study this object on itself for now. So let's see what kinds of matrices can appear for this representation. So monodromy constraints. Monodromy constraints and automorphisms. So the idea is the following. The idea is that I'm taking an origami and with a rich group of automorphisms. I gave you many examples of that. Regular origamis. And so I'm assuming this is not trivial, yes?
I didn't know if you want to write on the top one first.
Yes, I was waiting it for, well, but now it's too late, I guess. I'm going to save some time. So actually, this is a finite group, because automorphisms are translations, in particular holomorphic. So there are at most 84 G-1 such guys by Wollmilchsau. Okay, so it's a finite group. And so the remark is that so the affine homomorphisms act on G by conjugation. Why? The point is that if you conjugate a translation by an affine map, you get a translation. If you wish, you can see that at the level of derivative. So if you take an automorphism is a guy whose derivative is identity, is a translation. If you take an element of f and you conjugate, then the derivative, it's, well, the product. So derivative of f, derivative of this guy, which is identity, derivative f inverse, and so identity. Okay. Very good. So these guys act on conjugation. So actually, you have an action of f into the symmetric group of G. So it acts on G by permutations. So in particular, you can select f star finite index so that all elements of f star, this little subgroup, commute with G. Okay. So this is one remark. Another remark is that actually space here, H10, is, you already saw it, is a G module. So this is another name to say that we already had a representation on it, right? And so this means that we have a module, and f star commutes with this action. So it respects this structure of G module. So when you have this thing, there is a natural procedure which is try to decompose this space into what people call isotypical components for the representation. So you can see this on Serre's book. I mean, Serre is a big reference for many things in mathematics. And there is a book about linear representations, which is really cute. I mean, you should read about linear representations of finite groups. It's really beautiful. You should take a look. But so what I'm going to talk is basically contained there, but I'm going to give you a very brief description of facts that I need. So the idea is that you have G, and you can look at the irreducible representations of G, say over R. So these are irreducible G representations. Since it's a finite group, actually you can deduce them from the regular representation, so where you put a base vector for the element of the group and you generate a vector space and then you decompose into components. So these are irreducible representations. And actually, these facts that you commute allow you to decompose this guy into a sum over all irreducible representations of spaces W alpha. Okay, so, and this guy here is what people call isotypical component. Isotypical component. So it's basically the largest subspace where G acts by alpha, by the representation alpha. You collect all copies of alpha inside this guy. So these are the isotypical components. I mean, the copies of alpha are not well defined, but the isotypical component is something canonical. Okay, cool. So we are making progress on this thing. And now I want to recall you that in this book of Serre, for instance, you can find the classification of representations of finite groups. So there are only 3 types. So alpha can be a real representation. And so this means that the commuting algebra of this guy, so the endomorphisms of the vector space of the representation which commute with this guy is just scalars R. It can be complex. So the commuting. So this is what people call the commuting algebra. So the commuting algebra is C, and it can be quaternionic. So this is basically about classification of skew fields and things like that. Quaternionic. So this means that the commuting algebra is isomorphic to H, not the H of Chris. So it's H quaternionic like that.
Sorry, what is commuting algebra?
They are the matrix elements which commute with all matrices in the representation. So we have a representation from G to a vector space. In this vector space, you build all matrices, invertible or not, and you build an algebra of all guys which commute with this guy. And since it's irreducible, it can only be these 3 types. And so, why is this interesting? It's because if you look at this formalism, actually, what happens is a remark that I forgot to make here is that this property that F commutes with G tells you that F star O permutes W alphas. The fact that it commutes. And so this means that you can pick yet another finite index subgroup. I'm calling it 2 stars, just to make I did 2 operations. Respecting W alphas. So this means that I made a block decomposition of my cocycle in terms of reducible representations. And better than that, the fact that we know that these commuting algebras are like that have a nice interpretation. This means that the matrices, so this means actually that this means the following, that I think I broke it. I think it's here, but okay. Okay, so this means actually when you look at what this what I'm trying to say here is that if you take row, so if you take the matrices, so this is a way of saying I'm taking the matrices action homology of F(O), and I restrict them to W alpha, then I get a subgroup of either the symplectic group of our certain dimension over R for alpha real. I get some SUPQ for alpha complex. So this means the standard unitary, special unitary group with signature PQ. Or you get a fancy group which is called SO star something when alpha is quaternionic. No, this is just a bullet. So F star star, yeah, sorry. Yeah, actually I forgot to put them there, yeah, all right. So in this group here, just to give a quick definition, is you take matrices in G, L, H to the some power, which is this definition here, so that H strip H is identity, where H strip is basically transpose of a conjugate of sigma, except that you are not taking the usual conjugation in quaternions, but rather this bizarre thing here. You just change one sign. Okay, but so these are monodromy constraints. So you see, Kontsevich-Zorich cocycle matrices are rich. I mean, for those who know a little bit of algebraic geometry, it's kind of clear because there is always this variation of Hodge structure, etc. But if you are down to earth, you can already see that it's not any group of matrices, just a kind of special. And the remark is that if you want to find more about what kinds of matrices can appear, you should check Simeon Philip paper for more. Infos. Yes?
You are writing what's between the parentheses. This is the subsurface which is preserved by the representation.
Mm-hmm. Yeah, it's the isotypical component of
There's a piece of the surface which corresponds to the...
No. It's just a piece of the representation. I mean, I'm just breaking this. It's just a subspace of the homology. It's not no, it's not necessarily coming from a subsurface. No. Yeah, it could be. Yeah. Usually, it's more complicated than that. It's not so simple. So
Can you explain again the difference between F star and F star star?
F star star is just because this guy permutes, and so you take a finite index.
You cannot set an alpha to a beta. If you commute with the representation, don't you preserve the isotypical?
No, because I mean you need to be from this representation. Actually, you can build another one, which is to the exterior automorphisms, so out of this guy. And if you are in the kernel of that guy, then you really preserve. Because actually, when you apply alpha, you could change representations with the same dimension, the matching dimensions, and yeah, there's a little technical issue. It's not that important. I mean, forget about it. I mean, since it's up to finite index, it preserves. So you can take 1 star, 2 stars. Actually, the first time I wrote things about that, we put 3 stars in the paper, but yeah, I mean, it depends on, yeah. But the key answer is that, I mean, when you want to understand how irreducible permutations are, irreducible representations are permuted, you should look at the image in out of that group. And if it's trivial, then you don't permute the irreducible representations. Okay, so so I'm very happy I talked about monodromy. So you see that the matrices are very special. So now it's time to see why I'm interested in this cocycle. So let me give a motivation for you before talking about Lyapunov exponents. And now I'm going to be really fast. So If you don't, if you get lost, don't worry. It's on purpose. No, I'm joking. So motivation that I'm going to give is from Ehrenfest's Win3 model. So it's a model which they proposed, so Paul and Tatiana Ehrenfest in the 20s, more or less, if I remember correctly, the dates. So the Z2 periodic version is the following. So they were trying to understand how gases behave, and the idea to model gases is that you can replace them by billiards somehow. And the idea is that on the lattice Z2, you choose rectangles of size A and B, and you put such an obstacle on each integer point. So you periodically distribute these rectangles like that, and then you start playing billiard. So you come from here, from some point P, and then you run in some direction theta for some time, then you hit this guy, you reflect it with the usual law, then you come here, there, etc. And after some time, I'm going to give a name for this point as phi direction theta t of point P. Okay. Now, what physicists were interested in trying to understand was how fast these orbits go far from the initial point. So they have a notion of diffusion rate, which is simply the lim sup when t goes to infinity of log of the distance in R2, so plane distance, flat distance, between point at the origin and after time t over log t. Okay. It's not faster than linear, because I mean linear is the optimal stuff, so it's less than 1. And the question was, what is the diffusion rate for this thing? In the 80s, there were two physicists from Orsay. Hardy is not the Hardy from number theory, Hardy from physics. So in 1980, they conjecture that diffusion rate is different from 1/2. So they call this abnormal diffusion rate. Why abnormal? Because if you replace, so remark, if you replace rectangles by circles, then the billiard becomes chaotic. So the billiard becomes close to a random walk, or sort of Brownian motion, or it becomes chaotic from the point of view of dynamical systems. And for chaotic systems, so for random walks, you have central limit theorem, which you can translate to say that this number should be 1/2. It's about square root of t, the distance. And so abnormal is that the law is not normal, the normal law. So. Okay, and so this conjecture was open until recently. So there is a beautiful work by Vincent Lecroix, Hubert, and Lelièvre. And so if you want, if you want to play a prank with Vincent and Samuel, you can ask about this during Sage days rather than how to program in Sage. They proved that this diffusion rate is 2/3. In particular, different from 1/2, but it's more information. And to the day, the only explanation I have for this number is that it's a Lyapunov exponent of the Kontsevich-Zorich cocycle. And we have no elementary explanation for these 2/3. You can imagine, yes? This is for almost every p, so for almost every p, and that's it. In direction, almost every p, and all choices of. Actually, in the original paper, it was not like that, but then the theorem was refined, and p is the initial point. I mean, you don't want to pick silly points in some sense. I mean, yeah, and yeah, silly directions, yeah. for all. Okay. So I don't want to start at coordinates, for instance, because reflections on coordinates is quite hard to define and things like that. But so this is a Lyapunov exponent. So you might think that, well, those guys who found that were not thinking hard. Maybe there is an elementary way of doing that. They want to be very sophisticated, but there should be ways of doing that without this machinery of moduli spaces, blah, blah. But actually, if you replace the model by this model here, where you take out 1 square of each 4 and you replete, you get a very interesting diffusion rate. Sorry?
What is the floor?
Floor. 4. So you had 4,
Sorry, okay.
and you take 1 out. So the diffusion rate in this case becomes a very intuitive number. And this was proved by Delacroix and Zorich. So you see, if you try to cook up 2/3 out of 4 squares in position blah blah, forget it. You take 1 out, it becomes a complicated number. So there should be no easy explanation in principle for these numbers, except that they come from a beautiful theory of dynamics and moduli spaces. So this is the motivation. So now I have 15 minutes or maybe 20. Yeah, exactly. This is why I'm not putting dimensions, because, yeah. It's the same as before, in the sense that for almost every point in direction, but not. Yes, I have another bracket bar. Okay, so I want to use it. Up. Okay, so now I imagine that you are interested to know what are these Lyapunov exponents. And Lyapunov exponents are a construction that people from algebraic geometry are used to do, which is take relative versions of everything. I mean, if you do a little algebra, you see that they are all the time taking relative versions of objects. And in this case, the philosophy is that Lyapunov exponents, so K is cocycle, and Lyapunov exponents is what you get, is the relative version of matrices. So taking a single matrix, I'm putting like that, and eigenvalues. So formally, these Lyapunov exponents are simply limits along a certain sequence of elements of the affine F. So you take the norm of this guy, log, and then you measure how vectors grow with respect to the total growth of the matrix. So I'm just putting that for normalization reasons. And so these are the kind of limits. So these are Lyapunov exponents. I mean, there are theorems, also that's theorem ensuring that this kind of limits exist. And so what are those ANs? ANs are sequences of elements in affine of O. V is a vector in homology. And how do you pick these sequences? Well, there is a little point here. In principle, you should take sequences of affine elements that you see along orbits of GT. But it's not, it's true that in this case of origamis, you can play a different game. You can notice that F is countable. You can select a nice probability measure on F, actually with full support. So this means that the probability of picking an element here is positive for all elements. And these ANs are random products of elements of F. Okay, so it's not false. I mean, there is a theorem ensuring that in this case you can pretend that the geodesic flow is a really random walk. And for those who know a little bit, the names behind these things are Furstenberg, Kaymanovich, and Margulis, among others. Kaymanovich, Margulis, and other persons. And the idea is that in this context, you can prove that you can track geodesics by random walks with sublinear error. But well, this is just for experts. Okay, so these are the Lyapunov exponents. Mm-hmm.
So this is the Lyapunov exponent of the sequence AN? What does it depend on?
Theorem, it depends on nothing. No, it depends on, yeah, so the idea is that for almost all choices of this random product, so you get the same numbers, the same list of numbers. So actually, if you count multiplicities, you are going to get 2G numbers out of this list, because 2G is the dimension of the full homology. So this construction leads to 2G Lyapunov exponents, lambda 1, lambda 2, lambda 2G. Actually, the fact that I normalized my sequence in this way implies that lambda 1 is 1, and lambda 1 is 1. Another thing is that it's known that this inequality is always strict. This is that thing that I was mentioning, that in the part H10 the strength of the matrix is less than the other. But in general, there are inequalities here between these numbers. And actually, this last number is -1 because these matrices are symplectic. So rho AN belongs to the symplectic group of H1 OR. And symplectic matrices have the thing that if you take log of eigenvalues, they are symmetric with respect to the origin. So actually you have G exponents like that. Then you have lambda minus G, which is lambda G plus 1, etc. Okay, so this is the Lyapunov spectrum. And my claim is that this list of numbers that you get by looking at all vectors and doing this process is the same for almost every choice of ANs. So it does not depend much on many things. Okay, so these are the numbers. In particular, this 2/3 is one of these numbers here for some special case. And so what I want to say about Lyapunov exponents? Yeah, so there is a beautiful formula, asking Kontsevich-Zorich formula. That allows you to compute, well, allows you to compute the 2/3 in that case, and allows you to compute, in general, the sum of Lyapunov exponents of non-negative. I mean, of course, if I sum all exponents, I get 0. So this is, you can call it Matheus formula, but it's not so smart as asking Kontsevich-Zorich formula. And actually, it turns out that by using a very heavy machinery of computing degrees of the determinant of the Hodge bundle, etc., those guys figure out that the sum should be one classical term, which is basically coming from the adjunction formula. So it's basically sum of the kn plus 2 over kn plus 1. So people from algebraic geometry recognize more or less this 1 over 12 something. Kn, I remind you, it's the order of 0. So it describes the stratum where you are living. And then that would be it if the moduli space were compact. But then there is a boundary contribution which can be computed like that. So you compute the size of SL2ZO, so the SL2R orbit. And then for each element of the orbit, you write this element as a pair of permutations. And then you take one, and then you sum over cycles. So you take the horizontal permutation, take the cycles, and then you do 1 over length of the cycle. There is a geometric interpretation, but combinatorially it's like that. In particular, Sage can compute for you quickly the sum of Lyapunov exponents. Because all of these things are combinatorial, so Sage can, I told you that how to compute the SL2Z orbit out of those moves, Nielsen moves. And of course you can, I mean, computers can do that. And so this is a very practical formula, but the proof of this formula, it's a huge paper of more than 100 pages, if I remember correctly, using a lot of technology. So it's of course, I'm not going to give any hint on how you prove it. But what I'm going to do is a little application, if you wish. So let's compute the exponents of the Wollmilchsau.
Can you comment on the formula?
No. No, I'm sorry. No, it's just because, I mean, if I start trying to say things, then it's quickly becoming a very sophisticated discussion. I mean, these terms come from the adjunction formula, then this space is not compact, so compute the boundary contribution, then you have to do some flat determinants, and yeah, it's complicated. It's not. It's a huge paper. I mean, it's more than 100 pages just to get this formula. So.
Why is this so Why is there no multiplicity in the spectrum?
There are multiplicities in the spectrum. So I'm going to explain that in a moment if I manage to finish. So I'm going to give an example where there are multiplicities right now. Yeah. So actually, yeah. So this is a good remark actually. So let me point out before the application. So remark is that if you play this game of Lyapunov exponents for Matheus measures, so the measures that Pascal was talking about in the for Matheus measures. So Avila and Viana proved that these exponents are simple. So they have multiplicity 1. And in particular, yeah, so so they are like that. And actually, this part here, which implies that they can't be 0, was proved before by Forney in an important paper, which is actually the basis for this thing in some sense. I mean, Forney proved what people call the Kontsevich-Zorich formula, which is the beginning of this theory, and then you have to work with this formula until it becomes like that. I mean, the original formula by Kontsevich and Forney is not like that. So you have to manipulate until it gets so simple. I'm not going to define, but you can Google it. Pascal mentioned, but it's just for the sake of comparison. So actually, the first study, I mean, the first qualitative study of Lyapunov exponents were done for the Matheus measure, and those guys proved that there are no 0 exponents, and actually the multiplicity is 1. There is no repetition. So let's compute for the Wollmilchsau and see what happens. So let's change the measure. So computing for the Wollmilchsau means that you are looking at the measure which is supported on the SL2Z orbit, on that Riemann surface of finite volume. So instead of looking at the full moduli space, we are just computing Lyapunov exponents along a submanifold. And let's see if there are differences. So the Wollmilchsau, I remind you, it's something like that, right? 1i minus 1 minus I, then you multiply by j, so minus k, by I, so minus j, k, j. I asked an exercise. So what is the SL2Z? So first, this thing you can check is genus 3. It lives in H1, 1, 1, 1. Actually, the conical singularities are, you have one conical singularity for each class of plus minus g. So plus minus 1 gives the same singularity. Then plus minus I give another singularity, and you see the pattern. So there are 4. And they are all simple. You can do the turning around and see the total angle. So let's plug this thing in this formula. So you get that lambda 1 plus lambda 2 plus lambda 3 should be 1 over 12. Well, there are 4 times the same numbers. The ki's are all the same. So 4 times 1 times 3 over 2. It's 1, 3, and 2. Yes, right. Plus the orbit. Well, there is only one element in the orbit. That's the answer for the exercise. So the exercise asked you to show that actually the Veech group is everything. Okay, so there is only one element, so 1 over 1 times cycles. So how many cycles the horizontal permutation have? There are 2 cycles, so twice cycles of the same size, which is 4. So 1 over 4. Now I think we can do the calculation.
Can you say then what you wrote there?
1 over?
The last part I cannot see.
1 over 4.
No. The 1 over 1?
Yes, 1 over 1 is the length of this.
Just read it out. Just read it out.
1 over 1 times 2 times 1 over 4.
Thank you.
And so this is 1/2 plus 1/2, and it's 1. But lambda 1 is 1. And these numbers are non-negative. So what this means? This means that lambda 2 and lambda 3 are 0. And so actually this was the solution to a question of Veech. Veech was when Forn improved the non-uniform hyperbolicity of the Matheus measure. He asked if for other measures there could be a different partner for the exponents, and here's the answer. It can be 0 and with multiplicity. 0 twice. I mean, actually 4 times because you should repeat on the other side. So it's very different. So when you change from measures, the behavior is very different. I think I have 5 minutes or? Okay, so I'll take less than 5 minutes actually, just to tell you how to reach the same conclusion, maybe in 2 ways. Let's see if I have time, from more elementary methods. Yeah, I used the asking Kontsevich just as an excuse to talk about it, but actually don't need it for the application. So let's see. So for this particular case, actually you can figure out everything from the theory that I gave you about monodromy constraints. Because the Wollmilchsau, the automorphism group is the quaternions. And for the quaternions, you know the character table, so you know the irreducible representations. So all representations are, there are 5 of them. I mean, there are one representation for each conjugacy class. And there are 5, because this -1 is in the center, so 1, 2, 3, 4, 5. And there is a unique representation of dimension 4, which is the quaternionic representation, which if you represent on the regular representation is just 1 minus 1, I minus I, and you see. So you can form 4 vectors like that, and this is it. And so these representations here are real, and this is quaternionic. Well, it goes well with the name of the group, so quaternionic. And so if you do the analysis I was talking about before, this means that the action of rho of many stars here. I don't know how many stars do you want, Barak, but 3, 4, I don't know. But this means that the action on the H10, which is a space of dimension 4, I mean the dimension of this space is 2G minus 2, G is 3, so this is 4. So this is a subgroup of one of those SO stars. And if you look at it, it's the group SO star 2. But what is SO star 2 is simply, it's simply a number in the quaternionic space. So with that condition that sigma A minus BA plus CJ plus DK times A plus BI plus CJ plus DK equals 1. And you can check that by working what this relation means. You can check that actually this is a subset of A plus BI, so that A squared plus B squared is equal to 1, which is compact. So in other words, you are acting on a 4-dimensional space basically by multiplying, after putting the bases in the quaternion, the 4 vectors as I, j, and k, you are acting by multiplication by some compact group of numbers. And so this means that there is no growth in that formula for the Lyapunov exponent. The norm does not grow because it's compact. So the numerator is bounded and the other one grows. So it's 0. So this implies that lambda 2 and lambda 3 are 0. And to conclude, let me show. It's by looking at the character table. So the idea is that H10 is the part where -1, the element, the automorphism -1, acts by minus identity. And if you look at the character table, there is only one character when -1 acts by minus identity, which is this one. So so in other words, this guy here is the isotypical component of chi2. That's what I'm saying. But it's just looking at how the automorphism acts. And the fancy way of getting this thing is by relating Wollmilchsau to families of algebraic curves. So actually, you can write equations for the Riemann surface and this guy here. What happens for this family is that if you change this polynomial into x minus x1, x minus x2, x minus x3, x minus x4, then you get the full SL2R orbit of this origami. And over this family, the Jacobians of this Riemann surface have a fixed part. In other words, if you do the Hodge decomposition, actually, the basis of differentials of this guy has one part missing. So it's just like that. So there is no 1 over y. And this means that the homology, this means that actually this gives a fixed part in the Jacobian, and this explains why the matrices are acting by compact groups. But this is the advanced explanation for some of you which might know what variations of Hodge structure is. So what I'm saying is that there are at least 3 ways of recovering this fact: asking Kontsevich-Zorich formula, monodromy constraints, and variations of Hodge structures. And I think that's it. Thank you very much.